million, 16 machines, and they went slower. They lost. It was a race, a database race. Best implementation versus interface. You'd think the fast code would win, the better engine. But the real power is never under the hood. It's in the design, in the thinking, in the interface. Interfaces are powerful. They are the boundaries where our components interact to exchange information through the function signatures exposed by our implementation. But as boundaries, interfaces are not only what's exposed, but what's imposed. And therefore, not only how our systems talk, but how they scale. As engineers, we tend to think of performance in terms of systems coding, so all the low-level techniques. But I want to convince you that these techniques pale in comparison to the power of systems thinking. So to convince you of this, I want to give us a challenge. We're going to take one of the world's most valuable workloads in existence today, and we're going to show from theory and practice, first, that popular database management systems have a performance limit for this workload. Second, that this performance limit is a property of the interface, not the implementation, so that no amount of optimization or hardware, no amount of hardware, whether vertical or horizontal, will make these systems faster. And third, that this limit is far lower than we think and easy to hit. So having established this from theory and practice, that the interface more than code or compute sets the speed limit, we're going to find a way by fixing only the interface to make the system 10 times, 1,000 times faster, to prove the power of an interface for performance. And not because we feel the need for speed, or because it's our duty, but because the world demands it. So before we continue, just a heads up, we're going to start slow. We're going to finish fast, and that flash photography is allowed. But you might want to have your camera ready. You might want to get it out and have it ready when the time comes. So are you ready? Yeah. Great. So I said it's a challenge because the interface I have in mind for us, it's valuable. It's seen a ton of scrutiny. It's been Jepsoned 1,000 times over. We're going to have to find something hiding in plain sight that will look obvious in hindsight. And especially because when you think of a database, it's hard to find an interface more powerful than SQL. But the interface we're going to look at, it's more than SQL. So it's the intersection of SQL, and I'm being very specific here. So this is not a problem with SQL. It's a problem at the intersection of SQL across the network for transaction processing, or OLTP. So the workload executes transactions across the network between two or more rows to update counts. We're computing counts as goods and services move from one person or place to another. And in parallel to the movement of these goods and services, money is changing hands. This is not about SQL or networking in a general purpose OLGP or analytical OLAP context to store user tables or product tables or to run reporting. None of the control plane or data science workloads, like signing up a user, updating a product catalog, or querying, Parquet. Rather, the tables we have in view are strictly a subset of the tables you might find in a general-purpose database. So not the low-volume tables, but the high-volume tables, and specifically the inventory counts, the shopping cart items, the checkout payments, the deliveries, the refunds, the ratings, all the data plane processing that is Black Friday. If OLAP is read-heavy, then OLTP is write-heavy. So the field of transaction processing was pioneered by Turing Award winner Jim Gray. He's regrettably no longer with us. 50 years ago, at IBM, he worked on System R, the first implementation of SQL. 42 years ago, with Andreas Reuter, Jim coined the term ACID, and later wrote the book on OLTP. But 40 years ago, this year, Jim Gray would define a measure of transaction processing power in this paper, which he published under Tandem, not his own name. Benchmark wars were risky business at the time. So the paper would do two things. As I said, first, kickstart a benchmark war. That would actually, sometimes we need these things. We get stuck with performance, and then we actually need to go faster. So this is what this paper did. It got databases to get order of magnitude faster as a result, because this paper would encourage databases not only to be correct, but to be correct and fast. And the paper accomplished that. The second thing this paper accomplished was that Jim Gray would define the unit of a transaction. What is a transaction? And this unit was a debit credit, which remained his measure of transactions per second ever since. So there's some fascinating papers reflecting back on this 20 years later, one that he wrote, others that people wrote in tribute to Jim Gray, all talking about this. It's so wonderful to read, you know, their reflections. DeWitt authors one of these papers. Just so much wonderful anecdotes in there, all about Jim Gray. But all through his life, you know, what is the unit of a transaction? A debit credit. So simple, yet powerful. And powerful because you can express the movement of anything in life, the movement of anything, from one entity to another. The essence of a transaction. What does it mean to transact? It's to move something. And if this sounds simple, I think that's because it is. So to debit one row or account and to credit another. So in pseudocode, Gray wrote this out, says to update two accounts, insert a record of the history of the transfer, and then he did something subtle. This is often missed in industry, in research. It's incredibly subtle. Can you see what it is? He introduced the concept of a branch. Doesn't mean anything by itself, but it's essentially a hot account. So every transaction is going to go through this hot account, and it will be involved in some percentage of transactions. In other words, contention. So contention is where multiple transactions need to update the same rows, forcing the database to serialize or coordinate them. For example, here are 53 accounts or rows. These are just rows in a table. If we do double entry transactions between pairs of rows, but none of these transactions intersect, then there's no contention. Transactions can be executed by the database in parallel. But if we now process 34 transactions and 17 of them all hit the company bank account or income account or a stock item that's a bestseller, contention is now at 50%. So you sometimes hear even database engineers describe this as pathological. I've actually had a very senior database engineer wanted to interview with TigerBeetle. They were from a very well-known database company, and they said to me, "Oh, this workload is pathological." And I thought that's interesting, because Jim Gray didn't recognize contention as essential to the OLTP workload just to make it hard for us as database engineers. He wasn't trying to be pathological. Rather, he was saying this is the real world out there for OLTP, to make it realistic. Because the more people who want the same thing at the same time, the worse this gets, and queues build up. So these are the big scale events. If you think of big scale, think of contention. You can't really handle big scale if you can't handle contention. So you get a supernode in your graph, and contention approaches 90%. So you can imagine 14 million people last year trying to get tickets for Oasis, and it's sold out in minutes. There's always some degree of contention, but the more popular a platform gets and the more scale it attracts, the more you see the power law kicking in as power users flock to the platform. So you get these supernodes in the graph. Another name for the power law is the Pareto principle, where 80% of transactions say, just as an example, they might be by 20% of users. 80% of volume is from a small set of power users. And you tend to find the Pareto principle or power law everywhere, in all kinds of transaction workloads. You can go onto Wikipedia, and it's amazing, how many studies there are where you actually see in all of life, biology, geography. There's these things that tend to dominate. But in trading, if you take the trading volume, say for NASDAQ, and look at the top super stocks, so NVIDIA, Microsoft, Apple, Amazon, Google, depending on the day, they can dominate volumes together. The result of the power law in general is a large volume of transactions flowing through a small proportion of rows in the database, locking these rows, locking performance for as long as the locks are held. So Jim Gray understood that our OLTP benchmark should reflect contention, because a database transaction represents a debit credit in the real world. And indeed, if we trace the family tree of databases, they more or less go back to the banking, the brokerage, airline, manufacturing, inventory, ordering, shipping systems that did the equivalent of debit credit as original workload. High volume, but routine. These are not the complex queries of general purpose analytics. Not trying to get data out of the database. They're just trying to put transactions in, put data in. Very routine, high volume. So this pattern laid the foundation for OLTP. Today in industry and research, we tend to forget this, but transactions are all around us, everywhere, and they've been increasing in volume. So in the last 7 to 10 years, transaction volumes across gaming, energy, even ride sharing, they increased 2 to 3 orders of magnitude. In the extreme, real-time transactions or instant payments are up 4 orders of magnitude, or 10,000x, from what they were 10 years ago. Jeff Dean has a saying that you design for 10x growth, but plan to rewrite before 100x. So if our transaction volumes are up, how are we doing with our planning? Do our databases have enough power to process these volumes? So to answer the question, we're going to use the debit credit measure of transaction power as defined by Jim Gray. We're going to benchmark 4 databases, 2 with the same interface but different implementation, and then 2 with a different interface. So we're going to look at the power of an interface to unlock performance, but first we're going to look at the power of an interface to lock performance. And to do that, we're going to start with the crowd favorite. Any guesses? Postgres, world's most popular general purpose database by far. Postgres, our first contestant. You see echoes of Jim Gray's understanding of debit credit in the Postgres docs, in their canonical example of a transaction. However, the example here collapses debit and credit columns into a single balance, so it's single entry, not double entry. And it doesn't insert a record of the transfer as history, so it loses information. So instead, for our challenge, here's how we're going to represent Jim Gray's debit credit, his measure of transaction processing power. So first, we do a round trip across the network. We ask the database for Alice and Bob's account. Then we move this data back to the code where we check invariance. For example, does Alice have enough money? And maybe has Bob not been paid enough times in all these examples? If the round trip time is 1 millisecond, then the query takes 1 millisecond there and back again. Next, we send another query to the database to add to Alice's debits column and to add to Bob's credits column, and insert a record of the transfer as history. Taking another millisecond across the network, if we assume the database is infinitely fast, that's how much time it takes, and that's it. So this is what's called an interactive transaction, because the application interacts with the database across the network with multiple queries to move the data to the code. When you look at real systems, they might do more logic, so there may be more than 2 queries, as many as 10 in real systems, even for an optimal system. And while you can do this in one shot, in one query, it's not common. The 2 queries here also mirror the 2 messages in Jim Gray's pseudocode. First to read the accounts and then to write them back, plus a history. So I think this strikes the sweet spot. not as easy as one shot, yet not as hard as it could be. So if we send this workload into Postgres, a whole lot of transactions concurrently, how many transactions per second do you think Postgres will do? Okay, so I think 12,000 debit credits a second should be enough for anyone. Okay, well, this is fine. But what's happening? 41? I'm not clicking anything. So we're not changing anything in the application or database here. But over time, a few power users started showing up. Our workload shifted dynamically outside the database, outside the application, to a few hot accounts. And our DBA moved one of our database clients from 1 millisecond away to 10 milliseconds away. So did you expect contention and network latency to impact Postgres throughput like this? Let's take a closer look. So here we've got a Postgres server in Europe. Amsterdam doesn't have much space. We tried to get one here, but we had to settle for Frankfurt. So all the database clients are 1 millisecond away. And as we increase contention from 0 to 10% contention, 10% of transactions are hitting the same account, same row. As we go from 10% to 50% to 90% contention, we see throughput drop. I think this makes sense. But the surprising thing is how sensitive the Postgres interface is to network latency, where we position the clients. So here, we move the clients to be 10 milliseconds away from the server, and this reduces throughput significantly. But worse, faraway clients are now affecting the throughput of clients nearby. So the whole system is horribly intertwined. If you look closer at the interface, can you see the problem? More specifically, locks are being held. They're halting throughput, not only while transactions are being processed, this is the rub, not only while they're being processed in the database, but also while the database waits on the application to make a decision to commit. So this means waiting on a network round trip to send the accounts to the application and then wait for the application to send the commit. In other words, this transaction locks these rows for how long? 1 millisecond, if your network round trip is 1 millisecond. But if your network round trip is 10 millisecond, now your transaction locks these for 10 milliseconds. Why? There's a law to describe this effect, though. You see it typically applied in parallel computing, but Amdahl's law states that even with massive parallel processing, the maximum speed up we can achieve will be ultimately constrained by the serial or contended portion of the workload. That will dominate. So the law takes two variables, just two, the time that a transaction holds locks, the percentage contention in the workload. The law takes two variables, and then it plugs it into a simple formula to tell you the theoretical speed limit. And the scary thing is that even if your database is infinitely fast, infinitely parallel, and Amdahl's law assumes that it is. Even so, if the round trip is 1 millisecond and if contention is only 1 millisecond, then the theoretical speed limit is 100,000 transactions per second if your database is infinitely fast. But as contention increases, just 10%, throughput drops, not by 10%, but by 10 times. So as you go from 0% contention to 10% contention, you lost 10x throughput. Now you're at 10,000 TPS. At 50% contention, our theoretical top speed is 2,000 TPS. With power law contention, our top speed is 1,111 TPS. Theoretically, your database is infinitely fast, infinitely parallel. This is you cannot beat this theory. And that's just with a network latency of 1 millisecond. But if your clients are 10 milliseconds away from the database, this drops throughput another 10x. Let's do that again. Now we're at 10,000 TPS with 10% contention, then 1,000, then 200, And finally, 111 TPS is our maximum theoretical top speed for the Postgres interface. And again, these speed limits assume that your database is infinitely parallel and infinitely fast. I will never need to do more than 111 TPS, they say, because that is actually now the speed limit. So at this point, we should note that we're not the first to see that there's a major problem with the general purpose database interface for OLTP. That you hit this hard asymptote when you hold locks across the network. Unfortunately, you sometimes see two responses here, where making trade-offs instead of challenging assumptions, people give up on Jim Gray's vision of correct and fast. They fall for the temptation to be correct but not fast, or fast but not correct. So for example, they say that we should shift responsibility for scale from the database, where it's traditionally been, to the app. And then they say that the app shouldn't update the same key concurrently. You shouldn't be booking Oasis. Some other app should do that, but not your app. And they will say scalable apps. Did you notice that? They're like a scalable app. It's almost, it's really shifting that responsibility. I really hate that phrase when someone says scalable app. As a database developer, no, the platform should be scalable. We shouldn't be shirking our responsibility to the apps. The apps are stateless. We are supposed to be scaling our state as databases. But they say scalable apps must avoid contention, as if they even can. This is the real workload, or they say that you should trade ACID. Just trade ACID. Trade those guarantees for performance to relax the eye in ACID. Kyle was sort of hinting at this, these relaxed, weakened isolation levels. People actually say you should do this. I don't think we should listen to them. But because what they are essentially saying is, let the transactions use the wrong numbers and you will get more performance. But give me serializable or give me death. Because if you can't count correctly with contention at high speed, it's not OLTP. And if you're not doing serializable, if you're cutting corners on isolation, it's not ACID. So it's not OLTP or it's not ACID. As Uncle Ben would say, those who would trade safety for performance deserve neither safety nor performance, because you will never get performance by giving up ACID. You can try it, but you're not going to go much faster. Maybe a little bit, but it's wrong. So I think that's true. Until we challenge our assumptions, until I learn to think, for myself, I'm not going to be able to apply first principles to discover that there's a third way out. Of course, in spite of everything we've said, someone will suggest that there's a fourth way out, that you can make a trade-off between theory and horizontal scalability. So that the problem is really just Postgres, the specific implementation of Postgres. But if you use one of the newer cloud databases with a different implementation, then you can you can add machines to scale horizontally, and add as many machines as you like. And I quote, for unlimited, infinite scale. We've anonymized these vendors. You will never be able to guess who they are. This sounds exciting. This is more ambitious than 1000x. 1000x is child's play. It is so humble. Unlimited, infinite. And perhaps it sounds a bit expensive, but what if we swap out implementation and see what happens? Because the advantage of all these databases being wire compatible with Postgres as they are, is that the interface is the same, and therefore you can control the experiment. So what we're going to do is pick one of these to be contestant number 2. I'm not going to tell you which one, because it's not open source, and because the findings apply more or less to all of them, and there are quite a few of them. But we're going to launch a cluster that's fully managed on their cloud platform. They're going to run it for us, and you can do this with almost any Postgres provider out there. So the database looks like Postgres and talks like Postgres with the same interface, but otherwise it's a completely independent implementation. So where Postgres runs on one machine, this runs on many, which is supposed to give you more scale. So to embrace infinite scale, we ordered the largest possible cluster which immediately collided with finite procurement. So the next biggest we could get was 16 machines, costing $84,000 a month, or just over $1 million a year. To be honest, we had goosebumps. And I've anonymized these specs a little bit so you can really not guess which provider this is. But we had goosebumps because the same amount of money would buy you a McLaren. But does it scale? So we revved it up. We took it for a test drive. It felt amazing. We ran the same OLTP workload. This was through the same interface, but now powered by $1 million cluster. And the results were stunning. Okay, before I show you the results, let's think about it. So remember, 30-year-old Postgres on a single machine, very cheap, could do a speed, top speed of 12,000 debit credits a second, no contention. What do we expect from a modern rewrite, state-of-the-art rewrite, running on 16 times as many machines? 10x? Who says 10x? I'm saying 10x. Who says worse? Raise your hands. Who didn't raise their hand? Okay, 7,000 TPS. Zero contention. So we couldn't do 10x, but we could do a little more than half. So the best we could do was 7,524 transactions a second. And to be clear, these numbers were produced under identical workloads and controlled conditions. We're going to say a little bit more about this later. Perhaps someone might say that this is just the cost of consensus. In other words, that little split-second automated failover that happens only when the primary machine crashes. There shouldn't be any leader election going on here. We're not crashing machines. The cluster is stable. It's only doing replication within the same data center. These days, you get a ton of network bandwidth. We might expect a 4 to 5% hit from replication. This is what you typically measure, but not a 40 to 50% hit like this. There's got to be something else going on. Now, we've increased contention to 10%. Before it was 0% contention, we were half Postgres. Now we're a little bit more realistic, 10% contention, and we've lost 10x performance. We're now at 574 transactions a second. This is fine, they say, because our company will never do more than 574 transactions a second. But the good news of horizontal scaling is that the cluster is elastic. So you can change the number of machines to increase scale while decreasing cost, to do more with less. Here we've decreased the number of machines. We've cut cost by 50%. We've increased performance by 10%. This is staff engineering. We've cut our McLaren in half, and our engine's revving faster than before. So let's put the pedal to the metal and scale to one machine. This is principal engineering. We've decreased costs by 8 times and increased performance by 30%. If we put this all together and plot more contention for 50% and 90% power law, then we see that a cluster of 1 beats a McLaren. But if we plot Amdahl's law, then you really start to see that all these curves follow the theory, the same shape. If the interface imposes a speed limit, then all the money in the world can't overcome the asymptote. But if all that was left of you was your smile and some systems thinking, you can scale the world with your little finger. So you don't need a McLaren. Understanding is worth more. To be clear, this is bigger than Postgres. It's even bigger than SQL for that matter. So SQL is just a query language. Doesn't say anything about rolocks. Even if SQL were replaced with a better spec, if your database is general purpose to move the data to the code, then you need coordination in some shape or form, and this is what invokes Amdahl's law, because the network trip, that round trip time is never going to change. Speed of light in fiber is a constant, so write contention is the Achilles heel in the OLTP workload. It's what separates OLTP from OLGP, the volume of writes and the contention of these writes. But the worst is that if we measure one level deeper, if we put our McLaren back together and we take a look at those engines, they were never revving. Just 10% contention, the machines are idle. $1 million of hardware. is idle at 12% CPU. Of course, someone will insist that we should have tried harder to saturate the CPU, that we should have used static memory allocation, zero-deserialization, zero-copy, direct memory access, memory locality, cache line alignment, explicit limits, concurrency, parallelism, pipeline scheduling, hardware acceleration, branch prediction, vectorization, loop unrolling, profiling, IO ring, watch more Casey, and maybe if we had rewritten the database in. So I went looking for Mike Acton, one of the proponents of data-oriented design. I went looking for Mike, and I went to Maui, and I also got the shirt. But the point is that not even the most powerful techniques we use as systems coders, not even the most powerful systems techniques like data-oriented design they can't overcome a bad interface if the interface is the bottleneck. So we're going to have to take this off and find another way, because especially with the fast implementation, if it can drive the CPU, then you need to throw a lot of information at it to saturate it, and for that you need a powerful interface. So to go from 80% to 90, from 10x to 1,000, we need more than systems coding. We need systems thinking to fix the interface and break the sound barrier. So how can we fix the interface? By now, someone is asking. What are they asking? But what about? Stored procedures, thank you. So why not replace the queries, with custom functions in the database? So we transact in a single round trip across the network, but without row-locks. To this I say, let's take it a step further. With stored procedures, we still have to cross the network to call them. What if we didn't have to? What would be cooler than stored procedures? And the answer, of course, putting the Amsterdam in OLAP, contestant number 3 is DuckDB, an embedded analytical database that runs in process. So there's no network, so you transact directly against the database. What's interesting is that compared to the elephants, DuckDB's implementation specializes in the opposite direction. How to query a database, get information out, not how to put information in. That's what transaction processing is all about. So why are we even doing this experiment? I mean, we expect the implementation to be slower, right? But the interface should be more powerful because there's no network. It's embedded, it's in process, no locks across the network. Stored procedures on steroids. So to test switching interface like this to benchmark the speed of light, we gave DuckDB literally a pSQL file. It's a batch of transactions, one after the other to ingest. This takes stored procedures to a whole nother level because now the database has a batch of transactions to execute. Before, stored procedures are typically executed one after another. There's no batching. And again, this is just a simple experiment. We're just trying to get our intuition, on the speed up. Any ideas for what this? Are we going to go faster, go slower? Why would we go faster with an OLAP database? No. Okay, interface. Okay, good. So this pSQL batch is 90% contention, but DuckDB does 2,000 transactions a second, and this is a columnar database. To be clear, I'm not trying to recommend, DuckDB for transaction processing. I don't know what that says about the others, but I want to show what an embedded lock-free interface can do. And of course, you could give Postgres a pSQL file too, and I'm sure Postgres would beat this. But the fact that DuckDB is not an OLTP database is why it's so powerful and interesting, I think, as a control. So how does this compare with Postgres? As soon as you have 10% contention, the two OLGPs, they deteriorate. Even DuckDB as an OLAP database gets 10x more consistent OLTP performance. It's immune to contention at the network level because the embedded interface doesn't hold row locks. So Postgres beats the horizontally scaled Postgres-compatible cluster, also costs a bit less. And this is because the proprietary cluster holds locks not only between the client and server, but also across the horizontal partitions, to double down on locks across the network, both externally and internally, as above, so below. But as you go from 1 millisecond to 10 millisecond round trip, OLGP performance drops drastically again, and each time you increase latency. That's why running multi-region while it's advertised, it's not something you see often in practice, specifically for transaction processing, because the coordination across partitions is too sensitive. It's too vulnerable to network latency, so you have to trim your cables. And of course, none of this would be a surprise to you if you've read Frank McSherry's Scalability, but at what cost? So it's a paper you want not only your engineering team to read, but also procurement. So to recap, we've got 3 contestants, 2 with different implementations, the elephants, and a third with a different interface, the duck, gets us the 10x we'd expect also with stored procedures. However, with DuckDB, when we went embedded, we went to the extreme. So we threw out not only the Rolocks, but the network. So we coupled the database to a single server in the application layer. And while this is fine for analytics, and while this gave us 10x, giving up on the network cost us 2 things critical for OLTP. First, we lost multi-machine durability. You can't have your data just on one machine. So because there's no network, no replication, we need our transactions to be on more than one database replica. We don't want to lose them. Second, as a result of having lost durability, we lost availability. Without redundancy, there can be no fault tolerance and no automated failover if the primary fails. So is there a way to fix the interface to remove the locks but keep the network, therefore preserve durability and thus availability? If you could design a database today to specialize in transaction processing, not general purpose, not analytics, just transactions, what would it look like? Better yet, what would you call it? Of course, as we set out to create contestant number 4, to redesign the interface for transaction processing, we must acknowledge this paper by another Turing Award winner, the creator of Postgres, as well as the esteemed databaseologist from CMU, who, despite acknowledging SQL as the prevailing choice for database management systems, nevertheless predicted this very talk, that we would claim that the interface of Rolocks across the network is not sufficient for transaction processing. Of course, we know that the only reason our professors do this, to tell us not to do these things, is precisely because that's what they want us to go and do. And knowing that we would, they even advised us to learn from history, and so we did. We went digging, and we discovered this. So according to the winner of the Dutch Prize for ICT Research, Professor Dr. Hannes Mühlhausen, this is not a Dutch biscuit, but rather the oldest surviving transaction database, 5,000 years old, predating language, and demonstrating that while clay is immutable and while durability is solved, performance will drive databases to evolve. So what does the future evolution of transaction processing look like then? I want to suggest more like the workload. And here again, we learn from history. For a while, SQL as a language has been the language of databases for a pretty short time, 5 decades. The language of debit credit has been the language of transaction processing, at least in the real world, for centuries. So let's start with the theory, do a bit of back of the envelope. Let's check our workings. Debit credit over SQL, 2 round trips across the network, or 2 milliseconds per transfer. We're assuming the database is infinitely fast. What if our interface instead could take 1 round trip across the network, or 1 millisecond, but put 8,000 transactions or debit credits in this query? So let's even assume real processing time for this new design. So it's apples and oranges intentionally. We're going to process these 8,000 transactions in 20 milliseconds, for a total time of 21 milliseconds or 2 microseconds per transfer amortized. In theory, this would give a 1000x speed up, even compared to an infinitely fast database. So how does this look in practice? Again, recognizing that OLTP is high volume, high contention, but otherwise routine, we take the essential Jim Gray information of debit, credit, who paid or gave to who, and how much of what and why, and when and where. We take these essentially 2 CPU cache lines of information, 128 bytes. We pack as many of them as we happen to have at hand, or up to 8,000 of these in a single 1 megabyte query. We send this to the database. Then it processes these without holding rolocks across the network, acknowledges with a reply in a single round trip, and that's it. So we almost didn't do anything special. We studied the theory, the workload, and the interface. And of course, we listened to our professors. It's so simple, but this simplicity is composable and therefore flexible for any kind of transaction processing, whether financial or non-financial. It's just counting. So you can imagine that we didn't stop there, but that we might design everything in the database in this way. So as above, so below. To co-design everything in the internal implementation, the concurrency control, to amortize the internal latches, all those performance techniques I shared with you earlier, that we would also look at all the interfaces in the global consensus protocol, the local storage engine. For the entire database to be purpose-built like this from the ground up, a brand new modern database in a language of the future called Zig, that would become the most powerful language in the world with the best toolchain, and that we'd put in all the performance techniques and all the static memory allocation, assertion, and safety techniques of Tiger style to make this the fastest, safest database that we could possibly have implemented. But this is not a talk about implementation, is it? So in theory, this interface is powerful for transaction processing. A few caveats. It hyper-optimizes for one workload, but it's a widespread workload, OLTP. It's explicitly not a general purpose or analytics interface. Instead, as OLTP, it doesn't replace OLGP or OLAP, it complements them, specializing in the counting, in the numbers. So it's the Olympic 100 meters and nothing else. One might think that you lose consistency across your general purpose and transaction systems now that you have 2 databases, but you don't. Why? Because you put your user information in OLGP, the filing cabinet, and then the transactions by these users, you put them in OLTP, the bank vault. So you get a clean separation of concerns in your architecture. OLGP is your control plane database, OLTP is your data plane database, and critically also your system of record. Why? Because it's updated more frequently. So you hardly ever change a user's address. The string database is for that rare workload. But when a transaction comes in, if you have any data dependencies, you write these first to the respective systems, and then you commit the transaction to OLTP. If a transaction is in OLTP, you know you have all the data dependencies. OLTP is your commit record. So the only question remaining then is, now that we have 4 contestants, how do they compare? And how do we benchmark them? So all the benchmarks you're about to see, are you getting nervous now? We're doing benchmarks? All the benchmarks you're about to see were run on the same type of dedicated AWS instance, the i8G 16x large. The database server and the benchmark clients were on separate instances connected by dedicated 37 gigabit Ethernet link. The client sent transactions using the database's native bindings. We executed several warm-up iterations for each scenario to stabilize caches and buffers, followed by taking multiple measurements for a stable result. We checked a lot of things. This was weeks of benchmarking. There's a whole notebook of this. To control logical contention, the number of transactions using the same hot account, we generated batches with that degree of contention. We sent them concurrently to the database. So it's just those, that Jim Gray workload we've seen, the SQL, and we're just sending that concurrently in. We were careful to adjust the batch sizes so that we could stay between being open loop and closed loop. The reason is we didn't want to spike latencies if the database was clearly not handling the throughput, if it was low throughput. So we were somewhere between open and closed loop, a nice mix. Finally, we specifically chose Postgres and compatible databases because Postgres is so widespread. It is the benchmark. So we could keep the implementation anonymous, especially for the proprietary one, and we could stay away from benchmark wars with any specific commercial vendor. So we always double down on explaining these performance ideas from first principles, but I promised that we would put this into practice. And as has been the trend at Systems Distributed, performance benchmarks. So the time has come today to race. And what we're going to do now is literally we're going to take these performance traces. We ran all these databases. We collected a performance trace file, a timestamp, number of transactions processed, P100 for the batch. And I'm just going to play these for you on the screen, and we're going to compare them and see. This is just the real performance traces that we've captured. We captured many of them. So contestant number 1, Postgres. Let's start. This is the race. We're replaying the transactions. You can see we're doing about 300. Latency, P100 is around 200 millis. And this is actually what we're replaying now in real time. So Postgres had its first release in 1996. The hardware we're using costs $4,000 a month. It's got 0.5 terabyte of RAM, ton of CPU, huge network NVMe. You almost want to see the ref counter. So for this trace with 10% contention, Postgres is doing around 1,000 TPS with a P100 latency of 200. You can see the actual trace data running. There's our latency. And if we slot that real trace data, now you actually see a real dashboard. But, to be a race, we need a racing driver. There's Postgres. I think we need a racetrack too. And there goes Postgres, racing by itself, getting a head start. So I think we need another racer, don't you? Who shall we bring in? TigerBeetle. So you can see TigerBeetle's waiting patiently at the starting line. Postgres is doing laps. Postgres is on lap 4. And again, this is the real performance trace of Postgres. TigerBeetle's real performance trace isn't running yet. But it will start running as soon as we hit start. Maybe we wait a while. Postgres is almost halfway. So Postgres is on lap 6. Should we start TigerBeetle yet? Yeah, okay. I think we need a countdown. So 3, 2, 1. Catching up a little quickly. Okay. So TigerBeetle's doing 300,000 a second. That was so fast, you almost want to see a replay. What's happening? It's coming. This is the real Postgres speed from that trace file. What you're seeing here is simply we just put an interface on it. It's literally all you're seeing. We did have to slow down TigerBeetle by 10x. In the actual, TigerBeetle was so fast we couldn't visualize it for you, so we had to like make it artificially slower, but Postgres is real-time speed. Yeah, so in 10 seconds at 10% contention, TigerBeetle processed 3 million transactions, reaching a top speed of 400,000 transactions a second. And you know, that's with 20 secondary indexes enabled for TigerBeetle. So we traded some of the million plus TPS that TigerBeetle's engine can do. We traded some of that for full secondary indexing here. Worst latency was 305 millis to process 8,000 transactions at a time. If we'd let Postgres keep racing, would have taken 44 minutes. Postgres top speed 1,600. TigerBeetle's doing full replication and full consensus. It's running on a cluster of 4 machines. So, you know, it's doing all of that, and it's 266 times faster than Postgres, which is a single machine with no replication. So that's why it's important, I think, to insist that our databases are correct and fast. Because if you can design for performance like this, 1,000x performance, then you get more safety, not less. This is the power of an interface for performance. So the track we raced was called Super Circuit, in honor of Gene Amdahl, who dreamed in circuits fine. Just 10%, he warned, can choke the line. When locks and latches stall the rights and speedups fade despite the might, OLTP weeps, more is not always right. And that was just 10% contention. What happens if we dial it up? What happens if we dial it up to 50% contention? Mount Boom. Can you broker the movers and the shakers, match the volumes of the makers? So I'm sure we could if we had a Postgres compatible cluster, right? If we had horizontal scalability. Postgres cluster. So this, remember, this is Postgres. If it ain't horizontal, it's legacy. This was the best hardware we could get. This is the $1 million cluster. While it's slightly smaller spec, remember it's 4 times more scalable because we've got 4 times as many nodes. And here it is, the McLaren. 16 of the biggest machines we could get to spread the load horizontally. So TigerBeetle's running vertically. It's got replication across 4 machines, but we don't do horizontal scalabilities. TigerBeetle scales vertically with replication for durability. It's very simple. So TigerBeetle, yeah, it's a quarter of the size of this Postgres cluster, no sharding. Getting ready. So just to be sure that Postgres can't possibly lose, remember this is the infinite, unlimited scale cluster. Let's be sure that it can't possibly lose. We're going to give it a bit of a head start. Show respect. I'm just going to plug in a minute. 42 is the magic number. Okay, 0. Great. 42, great. So we're giving Postgres cluster a minute and 42 seconds head start. You can see it top right. You ready to get going on Mount Boom? Yeah, great. Off goes Postgres cluster. Off you go. We're going to shake the contention in this level to 50%. We're going to really feel it. Postgres is doing 100, let's call it 200 transactions a second. It's doing 200 transactions a second. Our company will never need to do that many transactions. $1 million cluster, we're scalable. We've done 4,000 so far. TigerBeetle's waiting at the starting line. Things are shaking. When we reach the time, TigerBeetle's going to start automatically by racer. So again, you can see bottom left corner, the racer here, this interface is literally, we're just playing performance traces. We did a whole lot of performance benchmarking, we captured these traces. We're just visualizing it for you with an interface. Power of an interface for understanding. Respect to Postgres cluster, P100 latency is 100 millis. But remember, we're tuning the batch sizes, so we're only sending in 10 transactions at a time, otherwise the latencies would just spike. They would break all those SLAs of like 1 second. It would be horrible. That's why we can really only send 10 at a time, because we're trying to be, remember, between open and closed loop. Off goes TigerBeetle. No problem with the contention. We've overtaken Postgres. You can see TigerBeetle's trace file bottom right. We're able to do batches of 8,000 at a time with the P100, pretty similar to Postgres, same order. So with contention of 50%, TigerBeetle is not 1,000 times faster, 2,400 times faster than the horizontal Postgres cluster, which would have taken, a day to do the same number of transactions. So that's resilience, that it tried that hard to keep going. Of course, to be fair to the Postgres cluster, its general purpose, or OLGP, it was not designed for OLTP, whereas TigerBeetle specializes only in OLTP and explicitly not for OLGP. It can't even execute OLGP queries, so it can't be benchmarked in reverse. So this is the power of an interface for performance. Shall we stop there? One more. Okay. So that was Mount Boom, 50% contention. What about Oasis? This is Galactica. Transactions at planetary proportions. This is the power law. 80% transactions by 20% of users, 90% contention. There are real systems in the world. For example, UPI, 85% of transactions go through one row, PhonePe. 50% go through PhonePe, the other 35% through Google Pay. 2 rows that dominate with 85%. A lot of these numbers are public, and you can get them. UPI's scale is staggering, instant payment system. And these systems are spreading to countries around the world, even to the US with FedNow. Let's see how we do. So we've raced the 2 elephants. And we've seen that TigerBeetle beat OLGP. But what about OLAP? What about an embedded database with no network or replication at all? So, of course, for our last race in Amsterdam, it's got to be DuckDB. So here, DuckDB running on the same hardware as TigerBeetle. TigerBeetle's doing full replication, DuckDB isn't. TigerBeetle's got high availability, consensus failover, all of that. And we're going to race the 2 at 90% contention. And because there are quite a few DuckDB people here in Amsterdam, and MotherDuck people, I need to be very careful. We need to be absolutely certain that DuckDB wins. So the Postgres cluster got a minute head start. That wasn't enough. DuckDB, we know, is already 10 times faster than OLGP at OLTP. So how much head start do we need to give DuckDB to be safe? I'm going to say 10 minutes. What do you all say? How many minutes shall we give DuckDB head start? 20. 20, 20, 20, 20, 20, 23. Anyone say more than 23? 60. I'm going with 23. Okay. How many seconds? 20, 25 seconds?
No, like 20 minutes, 25 seconds, because it's distributed systems 20, 25.
Okay, well, we committed on 23. It's a bit, yeah. How many seconds? 25 seconds? 19? Okay. And now, so we're going to have to wait 23 minutes because that is our head start. So we put a little feature in this racer. You will be able to use this race yourself. We will be releasing it, that you can actually upload your own database trace files and race different databases or different systems. Any kind of system, you can race them on this track. It's got the very cool feature called Let's Do the Time Warp. So we're going to do that, because otherwise we would be sitting here for 23 minutes. So what's going to happen is we're going to give DuckDB a little bit of a start, and then the racer itself will figure out from the 2 trace files just before contestant number 2 is going to start, and we'll time warp DuckDB to that point. Yeah. I heard someone say shame. That's a lot of head start. Okay. So yeah, for our third and final race, can I get a countdown?
3, 2, 1.
Off goes DuckDB. This is a massive track, massive scale. So DuckDB is already doing better than the Postgres clusters, and Postgres instance 1,800 transactions a second at 90% contention. This is a columnar database. This should not be happening, but DuckDB is outperforming OLGP. I told Hannes on the boat the other day, and they had never tried this. They were quite happy. We're about to do the time warp. About a ripple space-time. There it is. There's the time warp. DuckDB is now on its last lap, lap 10. TigerBeetle still hasn't started. So DuckDB has done nearly 2 million transactions after its head start. And if you look, top right, there's still about 40 seconds before TigerBeetle's going to get going. So when DuckDB gets around the dark side of the moon, it's just one stretch to the finish. It's that last little lap around the moon lap, and there's the finish line. You can see DuckDB flashing. It's getting excited, like it's on its last lap. It's pretty close to the end. Countdown with me. 7, 6, 5, 4, 3, 2, 1. 90% contention. TigerBeetle's throughput is the same. DuckDB is around the moon. It's skateboarding into the home stretch. TigerBeetle's third lap is complete. DuckDB is on its last lap. TigerBeetle's only halfway. DuckDB has the finish in sight. It's about to cross the intersection. TigerBeetle only on lap 7. DuckDB approaching the finish. This is real performance trace data. We're just playing with camera angles in Blender. So with 90% contention, full replication, TigerBeetle is 229 times faster than DuckDB, executing a P-SQL file in process. And DuckDB is 10 times faster again than the elephants. So we got about a 2,000 speed up here. And I think we can finish here. To rank the contestants, Tallest to fastest, which is the power of an interface for performance.